Hello friends, welcome to Knowledge Galaxy to rediscover the basics with Mayank Tiwari, a premier coaching and training channel dedicated to metallurgy studies and consultancy, established to cater the needs of students, degree, diploma and AM/IIM metallurgy, competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries and whosoever seeking knowledge and information about various subjects and topics of metallurgy, operational process optimization, productivity improvement analysis, concepts like 5S, total productive maintenance, TPM, quality circle, QC, root cause analysis, RCA, ISO systems, QMS, EMS and OSHAs, practical and effective communication English, written and spoken. This is the foundation stone of forming this channel. To impart practical industrial knowledge as per your specific requirements via tailor-made training sessions for your colleagues, employees and students, please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 101 for scheduling and organizing the sessions at your place or via video conferencing. My dear friends, you might have heard that training is costly, but not to train is still costlier. So do get your employees, colleagues and students trained on the relevant topics so that they perform well on their duty and subsequently contribute positively to the growth of your company and organization in a better way. So do contact me as soon as possible for organizing the sessions and get them trained. Dear friends, another important aspect of Knowledge Galaxy is that specialized subject-wise coaching classes are available for Diploma Engineering, Metallurgy and Mechanical, IIM, Indian Institute of Metals, Part 2 or Section B, and competitive and recruitment exams for GATE, SAIL and various other government and private sector companies. Metallurgical industries, here complete syllabus coverage will be offered for the students aspiring to appear in the forthcoming semester exams, that is December or June. So please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44 101 for scheduling and organizing the classes via video conferencing. My dear friends, now the technology has improved so much that actual physical distance doesn't matter anymore. You can get your doubts clarified and clear all your doubts and gain knowledge by sitting at your home or office or wherever you are comfortable with. So use the technology and get your doubts cleared. Do contact me as soon as possible. My dear friends, I have made so many videos which are available in my YouTube channel. So do visit my channel repeatedly and regularly and do watch all the videos available there from start to finish, as gaining less knowledge or having half knowledge is more dangerous than having no knowledge. So for the benefit of you all, please do watch all the videos from start to finish. Here I am very much thankful to all my subscribers who believe in me and like my content. So I again request all the persons to do subscribe my channel, like my videos and also share with your friends so that others can also gain knowledge about the topic. So currently I am going to discuss about in this video I am going to discuss about equilibrium diagrams. These are very much important from the perspective of metallurgical and material science. So do watch it very carefully and sincerely. You will get maximum of your doubts clear. This is, I am very much hopeful for that. So let us start the presentation for today. Equilibrium diagrams or phase diagrams. Now let us see what it is, what are called equilibrium diagrams and what are called phase diagrams. So my dear friends, as we know so far that there are many possibilities for the structure of an alloy. I have made another separate video on the structure of an alloy, how the Hume-Rothery rule describes the formation of an alloy. You can watch it, which is available in my channel. Since the properties of a material depend to a large extent on the type, number, amount, and the form of the phases present and can be changed by altering these quantities, it is essential to know first the conditions under which these phases exist, and second the conditions under which a change in phase will occur. A great deal of information concerning the phase changes in many alloy systems has been accumulated, and the best method of recording the data is in the form of phase diagrams, also known as equilibrium diagrams or constitutional diagrams. In order to specify completely the state of a system in equilibrium, it is necessary to specify three independent variables. These variables, which are externally controllable, are temperature, pressure, and composition. With pressure assumed to be constant at atmospheric value, the equilibrium diagram indicates the structural changes due to variation of temperature and composition. The diagram is essentially a graphical representation of an alloy system. Do remember this. Ideally, the phase diagram will show the phase relationships under equilibrium conditions, that is, under conditions in which there will be no change with time. Equilibrium conditions may be approached by extremely slow heating and cooling, so that if a phase change is to occur, sufficient time is allowed. In actual practice, phase changes tend to occur at slightly higher or lower temperatures depending upon the rate at which the alloy is heated or cooled. Rapid variation in temperature, which may prevent phase changes that would normally occur under equilibrium conditions, will distort the and sometimes limit the application of these diagrams. So let us have the introduction of the phase diagrams. Phase diagrams are an important tool in the armory of a materials scientist. In the simplest sense, a phase diagram demarcates regions of existence of various phases. So you can also correlate phase diagrams to a map, as the maps give and guide us to our desired location, and so the phase diagrams also guide us to the knowledge of about the various alloy systems. Phase diagrams are also referred to as equilibrium diagrams or constitutional diagrams. The usage requires special attention, though the term used is equilibrium. In practical terms, the equilibrium is not global equilibrium but microstructural level equilibrium. I do repeat this. Phase diagrams are also referred to as equilibrium diagrams or constitutional diagrams. The usage requires special attention, though the term used is equilibrium. In practical terms, the equilibrium is not global equilibrium but microstructural level equilibrium. So don't get confused with this. and clearly understand what is said for phase diagrams or equilibrium diagrams. Broadly, two kinds of phase diagrams can be differentiated. This is for a convenience of understanding point of view, those involving time and those which do not involve time. So, in presently we will be dealing with phase diagrams not involving time, and this type can be further subclassified into those with composition as a variable, example temperature versus percentage composition, and second, those without composition as a variable, example pressure versus temperature. Time temperature transformation, that is TTT diagrams, and continuous cooling transformation, that is CCT diagrams, involve time. These diagrams will be considered in separate presentation. So let us now discuss about some definitions which are very much useful and very much always used in the phase diagrams. So first, to start with, components of a system. Independent chemical species which comprise the system. These are called components of the system. These could be elements, ions, or compounds. Some of the examples are a aurum copper system, where components are aurum and copper, they are elements. Second is ice water system, where the components is H2O, that is compound. And next is example is Al2O3 and Cr2O3 system, where the components are Al2O3 and Cr2O3. Next term comes is phase. So let us see the definition of phase. A physically homogeneous and distinct portion of a material system, example gas, crystal, amorphous, etc. So let us consider each one in detail. Gases. Gaseous state always a single phase, that is even if it is mixed at atomic or molecule level. Second, liquids. Liquid solution is a single phase, that is NaCl in water, and liquid mixtures consists of two or more phases, example oil in water, which no mixing at the atomic level. Third is solids. In general, due to several compositions and crystal structures, many phases are possible. So for the same composition, different crystal structures represent different phases. Example is iron BCC and iron FCC, they are different phases. Let us continue with some more definitions. So what kinds of phases exist? So my dear friends, there are practically 6 types of phases that do exist. So let us discuss about them. First is based on state. They are gas, liquid and solid. Second, based on atomic order. They are called amorphous, quasi-crystalline and crystalline. Third is based on band structure, that is insulating, semiconducting, semi-metallic and metallic. And next one is based on property, paraelectric, ferromagnetic and superconducting. Next is based on stability, stable, metastable and unstable. Also sometimes based on size or geometry of an entity, that comes to nanocrystalline, mesoporous and layered. So now let us discuss about phase transformation. What is called a phase transformation? Phase transformation is the change of one phase into another. For example, when water turns to ice and alpha iron, that is BCC, turns to gamma iron FCC. They are called phase transformations. Grain. Another important point and aspect is grain. The single crystalline part of polycrystalline metal separated by similar entities by a grain boundary is known as grain. I hope it is clear to all of you. Some more definitions to continue. First, solute. The component of either a liquid or solid solution that is present to a lesser or minor extent, or you can also see that the component that is dissolved in the solvent. I hope it is clear to you all. Next is solvent, the component of either a liquid or solid solution that is present to a greater or major extent, and you can see that the component that dissolves the solute is called solvent. Next is system. System has two meanings. First, system may refer to a specific body of material or object, or it may relate to the series of possible alloys consisting of the same components but without regard to alloy composition. Solubility limit. For many alloy systems and at some specific temperatures, there is a maximum concentration of solute atoms that may be dissolved in the solvent to form a solid solution. This is called a solubility limit. Some more definitions to continue. Microstructure. So let us see the definition of microstructure. Phases plus defects plus residual stresses and their distribution. So this is broadly the microstructure, what consists of structures requiring magnifications in the region of 100 to 1000 times, or the distribution of phases and defects in a material. It is commonly called microstructure. Phase diagram. The definition of phase diagram is map that gives relationship between phases in equilibrium in a system as a function of temperature, pressure and composition. So as the map demarcating regions of stability of various phases. So you can get the knowledge and idea about the various phases and their stability and instability over different temperatures and concentration. So now let us discuss about variables or axes of phase diagrams. The axes can be thermodynamic, that is temperature, pressure and volume. And next is kinetic or composition variables, C or percentage X. In a single component system, unary system, the usual variables are temperature and pressure. In phase diagrams used in materials science, and usual variables are temperature and percentage composition. In the study of phase transformation kinetics, TTT diagrams or CCT diagrams are also used where the axes are temperature and kinetics. So some more definitions. System components. Phase diagrams and the systems they describe are often classified and named for the number in Latin of components in the system. So here in this table the different types of systems are given. That is, one is called, when the number of components is 1, the system is called unary, 2 binary, 3 ternary, 4 quaternary, 5 quinary, 6 sexenary, 7 septenary, 8 octenary, 9 nonary and 10 decennary. So these are the different nomenclatures used for different systems or diagrams. So now let us consider about unary phase diagrams. Let us discuss it in detail. Let us start with the simplest system possible, the unary system, wherein there is just one component. Though there are many possibilities even in unary phase diagrams in terms of the axes and phases, we shall only consider a temperature and pressure unary phase diagram. So this diagram is given as pressure in megapascals and temperature degree centigrade as 2x's. So different nomenclatures are mentioned in here. So let us describe each of them. Let us consider the water, that is H2O unary phase diagram. The Gibbs phase rule here is F is equal to C minus P plus 2. So 2 is for temperature and pressure. I hope you remember the Gibbs phase diagram, Gibbs phase rule, and if you have forgotten, you can refresh your knowledge by visiting my video which is available on my channel regarding the Gibbs phase rule. So you can check it that to refresh it. So no composition variables are available here. Next is along the two faces coexistence are at B and C, like you can see in this diagram B and C. Lines, the degrees of freedom F is 1, that is we can choose either temperature or pressure, and the other will be automatically fixed. The three-phase coexistence point at A. So this is the three-phase coexistence point at A. Are invariant points with F is equal to 0. Invariant point implies they are fixed for a given system. The single phase region at point D, you can see here D, temperature and pressure can both be varied while still being in the single phase region with F is equal to 2. I hope this diagram is very much clear to you, all of you. So unary phase diagrams, another description is here. You can see that here temperature and pressure in kilobars are used. The above figure represents the phase diagram for pure iron. The triple point temperature and pressure are at 490 degrees Celsius and 110 kilobars respectively. Alpha, gamma and epsilon refer to ferrite, austenite and epsilon iron respectively, and delta is simply the higher temperature designation of alpha. You can see the various nomenclatures used here. Binary phase diagrams. Let us now consider binary phase diagrams. Binary implies that there are two components. Pressure changes often have little effect on the equilibrium of solid phases unless, of course, we apply huge pressures. Hence, binary phase diagrams are usually drawn at 1 atmospheric pressure. The Gibbs phase rule is reduced to variables are reduced to F is equal to C minus P plus 1, that is 1 is for temperature only. Temperature and composition, these are the usual variables in materials phase diagrams. So phase rule for condensed phases comes to F is equal to C minus P plus 1. 1 is for temperature, so don't get confused. In the next page, we will consider the possible binary phase diagrams. These have been classified based on first, complete solubility in both liquid and solid states. Second, complete solubility in both liquid state but limited solubility in the solid state. And third, limited solubility in both liquid and solid states. So this is the overview of possible binary diagrams, binary phase diagrams. You can observe different nomenclatures and different phases present in that. So first let us consider complete solubility in both liquid and solid phase states. In liquid state it is called isomorphous system. So it is having further demarcations as isomorphous with ordering, and second is isomorphous with phase separation, and in solid state it is solid state analog of isomorphous. Next is complete solubility in liquid state but limited solubility in the solid state. They have two forms: in liquid state eutectic and in peritectic, and in solid state they are eutectoid and peritectoid. Next comes is limited solubility in both liquid and solid states. They have three types: monotectic, syntectic and metatectic. These are in the liquid state, and monotectoid in the solid state. I hope it is very much clear to you all. So now let us consider about the coordinates of phase diagrams. Phase diagrams are usually plotted with temperature in degrees centigrade or degrees Celsius or Fahrenheit as the ordinate and the alloy composition in weight percentages as the abscissa. The weight percentage of component A is equal to WA is equal to weight of component A divided by sum total of weight of all components into 100. Next comes is the atom or mole percentage of component A is given by XA is equal to number of atoms or moles of component A divided by sum total of number of atoms or moles of all components into 100. I hope these calculations are very much clear to you all. These are very much important. The conversion from weight percentage to atomic percentage may be made by the following formulas. So let us discuss that very carefully. Atomic percentage of A is equal to X divided by X plus Y into M by N into 100. So it comes to atomic percentage of B is equal to Y into M by N divided by X plus Y into M by N into 100, where M is the atomic weight of metal A and N is the atomic weight of metal B. Next is X is the weight percentage of metal A and Y is the weight percentage of metal B. There are some experimental methods to determine the phase diagrams. Let us consider thermal analysis. A plot is made of temperature versus time at constant composition. The resulting cooling curve will show a change in slope when a phase change occurs because of the evolution of heat by the phase change. This method seems to be best for determining the initial and final temperature of solidification. Phase changes occurring solely in the solid state generally involve only small heat changes, and other methods give more accurate results. Next method is metallographic methods. This method consists in heating samples of an alloy to different temperatures, waiting for equilibrium to be established, and then quickly cooling to retain their high temperature structure. The samples are then examined microscopically. This method is difficult to apply to metals at high temperatures because the rapidly cooled samples do not always retain their high temperature structure, and considerable skill is then required to interpret the observed microstructure correctly. Next method is X-ray diffraction. Since this method measures lattice's dimensions, it will indicate the appearance of a new phase either by the change in lattice dimensions or by the appearance of a new crystal structure. This method is simple, precise, and very useful in determining the changes in solid solubility with temperature. I hope all these methods are very much clear to you all. You should not have any doubt on them. I hope we are going so far so good. So now let us move on and study the classifications of equilibrium diagrams or phase diagrams. So equilibrium diagrams or phase diagrams may be classified as follows. First, components completely soluble in the liquid state. Second, completely soluble in solid state, that is type 1. This is the subtype of 1. Next is insoluble in the solid state, the eutectic reaction, that is type 2. Next is partly soluble in the solid state, that is the eutectic reaction, type 3. Fourth is formation of a congruent melting intermediate phases, that is type 4. Next, fifth is the peritectic reaction, type 5. Second type of classification is components partly soluble in the liquid state, the monotectic reaction, that is type 6. Third type is components insoluble in the liquid state and insoluble in the solid state. They form the type 7. Next is transformations in the solid state. There are many transformations which occur in the solid state. So what are they? Let us discuss. First is allotropic change. Next is order disorder change. Third is eutectoid reaction. And fourth is the peritectoid reaction. We will be discussing each of them in detail in the next detailed presentation. Now we will be discussing about in detail about the isomorphous phase diagram. Isomorphous phase diagrams form when there is complete solid and liquid solubility. Complete solid solubility implies that the crystal structure of the two components have to be same and Hume-Rothery rules are to be followed. I hope you remember the Hume-Rothery rules, and if you have forgotten, you can watch my video on Hume-Rothery rules which are available my channel, so you can visit that. Example of systems forming isomorphous systems are copper nickel, argentum aurum, germanium silicon, Al2O3 and Cr2O3 systems, etc. Both the liquid and solid contain the components A and B. In binary phase diagrams between two single phase regions, there will be a two phase region, that is, in the isomorphous diagram between the liquid and solid state, there is the liquid plus solid state. The liquid plus solid state is not a semi-solid state, that is, it is a solid of fixed composition and structure in equilibrium with a liquid of fixed composition and structure. In some systems, example aurum nickel system, there might be phase separation in the solid state, that is, the complete solid solubility criterion may not be followed. These will be considered as a variation of the isomorphous system with complete solubility in the solid and liquid state. These are the various cooling curves for isomorphous systems. We will discussing about each of them in detail. So let us discuss solidification or cooling curves. So this diagram is plotted against temperature and time. So for this pure metal, as you can see that when the solidification starts, the temperature falls, liquid and from liquid starts to solidify at a given particular temperature, and it solidifies completely at a single temperature only, and then it solidifies further as a complete solid when the further temperature is decreased. And in alloys, the solidification starts when the temperature is reduced. Solidification starts at a particular temperature and it ends at some other temperature. So there is a range of temperature over which the solidification completes. At one temperature, that is TL, the solidification begins, and the next temperature, that is TS, the solidification completes. And below this TS temperature, the metal is alloy system is completely solid, and above this TL temperature, the alloy system is completely liquid, and between this TL and TS temperatures, the alloy system having liquid plus solid both. I hope it is very much clear to you all. Isomorphous phase diagrams. Let us now discuss some in detail some more. Temperature and composition can both be varied while still being in the single phase region. So this can be seen from here as in the liquid case, where C is equal to 2, P is equal to 1, that is for liquid only, and F is equal to 2. And as you can see, this red line is for liquidus and this blue line is for solidus. Liquidus line implies that above this temperature the alloy system will be in liquid state, and this blue line solidus line implies that below this temperature line the alloy system will be in the solid state, and between these two lines the alloy system will be in liquid plus solid state. So as you can see, the various nomenclatures and various states are given mentioned here. At this temperature, at 1080 degrees Celsius temperature, there will be structure different, and here at 1457 degrees Celsius there will be C is equal to 1, P is equal to 2 and F is equal to 0. In between this liquid plus solid region, C is equal to 2, P is equal to 2, that is for liquid plus solid, and F is equal to 2. And in this solid region below solidus line, C is equal to 2, P is equal to 1, that is for solid only, and F is equal to 2. Here temperature and composition can both be varied while still being in the single phase region, and you can see that in this between these two liquidus and solidus lines, in the two phase region, if we fix temperature 1 and hence exhaust our degree of freedom, the composition of liquid and solid in equilibrium are automatically fixed, that is, we have no choice over them. Alternatively, we can use our degree of freedom to choose Cl, then T and temperature and composition are automatically fixed. Now let us discuss about the different solubilities. First, the type 1 is two metals completely soluble in the liquid and solid states. Since the two metals are completely soluble in the solid state, the only type of solid phase formed will be a substitutional solid solution. The two metals will generally have the same type of crystal structure and differ in atomic radii by less than 8%. The phase diagram consists of 2 points, 2 lines and 3 areas. I hope you still remember the structure of an element, structure of materials, which I have made a video separately on that, which is available in my channel. You can watch that. The 2 points TA and TB represent the freezing points of the two pure metals. So this is the phase diagram of two metals completely soluble in the liquid and the solid states. So this diagram depicts that whatever I have just explained, TA, TB, two different metals, the melting points of both the pure metals, composition, weight percentage of B, temperature is this axis. Above this line it is liquid solution, this is the liquidus line, this is the solidus line, below this line it is a solid solution alpha, and between this liquidus and solidus line there is liquid plus solid solution alpha, and this is the temperature T1 and T2. T1 is the liquidus temperature, T2 is the solidus temperature. The upper line obtained by connecting the points showing the beginning of solidification is called the liquidus line, and the lower line determined by connecting the points showing the completion of solidification is called the solidus line. This is the definition of the two lines which I have just explained. The area above the liquidus line is a single phase region, and an alloy in that region will consist of a homogeneous liquid solution. Similarly, the area below the solidus line is a single phase region, and any alloy in this region will consist of a homogeneous solid solution. I have explained all these things. It is common practice in the labeling of equilibrium diagrams to represent solid solutions and sometimes intermediate alloys by Greek letters. In this case, let us label the solid solution alpha. Uppercase letters such as A and B will be used to represent the pure metals. Between the liquidus and solidus line, there exists a two-phase region. Any alloy in this region will consist of a mixture of a liquid solution and a solute solution. Specification of temperature and composition of an alloy in a two-phase region indicates that the alloy consists of a mixture of two phases but does not give any information regarding this mixture. It is sometimes desirable to know the actual chemical composition and the relative amounts of the two phases that are present. In order to determine this information, it is necessary to apply two rules. Let us now discuss about these two rules in detail, each one by one. The first one is, rule 1 is chemical composition of phases. To determine the actual chemical composition of the phases of an alloy in equilibrium at any specified temperature in a two-phase region, draw a horizontal temperature line called a tie line to the boundaries of the field. These points of intersection are dropped to the baseline and the composition is read directly. This is known as the tie line rule. My dear friends, this is very much important, the tie line rule. For easy understanding, let us consider an alloy composed of 80A and 20B at the temperature T as shown in the figure in the next slide. The alloy is in a two-phase region. Applying rule 1, draw the tie line to the boundaries of the field. Point M, the intersection of the tie line with the solidus line when dropped to the baseline, gives the composition of the phase that exists at that boundary. In this case, the phase is a solid solution alpha of composition 90A and 10B. Similarly, point O when dropped to the baseline will give the composition of the other phase constituting the mixture, in this case the liquid solution of composition 74A and 26B. This is the diagram which I have just explained. Diagram showing the interpretation of the tie line MO drawn in the two-phase region at temperature T. This is the M and this is point the O, and this all I have just explained in the previous slides. So next rule is relative amounts of each phase. To determine the relative amounts of the two phases in equilibrium at any specified temperature in a two-phase region, draw a vertical line representing the alloy and a horizontal temperature line to the boundaries of the field. The vertical line will divide the horizontal line into two parts whose lengths are inversely proportional to the amount of the phases present. My dear friends, this is also known as the lever rule. My dear friends, here there are two different rules. One is the tie line rule and second is the lever rule, which seems to be very similar, but please don't get confused with them as both are different, as the lever rule depicts and describes about the relative amounts of each phases, and the tie line rule gives the actual amount of each phase in that particular temperature range. I hope it is clear to you all. The point where the vertical line intersects the horizontal line may be considered as the fulcrum of a lever system. The relative lengths of the lever arms multiplied by the amounts of the faces present must balance. For easy understanding, consider an alloy composed of 80A and 20B at the temperature T. The figure is shown in the next slide. The vertical line representing the alloy 20B divides the horizontal tie line into two parts, Mn and No. You will be seeing the picture in the next slide. Here are some details of that picture. If the entire length of the tie line MO is taken to represent 100% or the total weight of the two faces present at temperature T, the lever rule may be expressed mathematically as: first, liquid percent is equal to Mn divided by Mo into 100, and second, alpha, that is solid percentage, is alpha percent is equal to No divided by Mo into 100. So this is the diagram which shows the interpretation of lever rule drawn in the two-phase regions at temperature T. So you can very much see and observe this picture which I have just explained the details of it, and further more details are being explained in the coming slides. If the tie line is removed from the phase diagram and the numerical values are inserted, it will appear as shown in the figure of next slide. Applying the above equations, first, liquid percent comes to 10 divided by 16 into 100 is equal to 62.5%, and solid alpha percent is equal to 6 divided by 16 into 100 is equal to 37.5%. So this is the tie line MO removed from the figure of previous slide to illustrate the application of lever rule. So as you can see, this is the total length 16, amount of liquid is given by Mn, and amount of alpha is given by NaO. So here it comes as what I have just explained. To summarize both rules, the alloy of composition 80A and 20B at the temperature T consists of a mixture of two phases. One is liquid solution of composition 74A and 26B, constituting 62.5% of all the material present, and the other is a solid solution of composition 90A and 10B, making up 37.5% of all the materials present. I hope it is very much clear to you all, the computation of lever rule and the application of tie rule. So here are some more examples of the tie line and lever rule. You can pause the video and observe all the details of this slide and how to calculate the different amounts of different phases present by applying the tie line and lever rule. It is very much important because in many exams it is always asked how to determine the different quantities of phases present in the phase diagram. Let's move on. Variations and isomorphous system. Let us now consider about variations of isomorphous system. An alloy typically melts over a range of temperatures. However, there are special compositions which can melt at a single temperature like a pure metal. There is no difference in the liquid and solid compositions. It begins and ends solidification at a constant temperature with no change in composition, and its cooling curve will show a horizontal line. Such an alloy are shown as a congruent melting alloys and sometimes known as pseudo-eutectic alloy. Examples are CuAu and nickel PD. So this is the case A where and case B. So variables are temperature CLB, CSB is equal to 3, and these are the various depictions of the phase diagram. You can pause the video and observe it very carefully. Congruent melting alloys are just like a pure metal. Do remember this. And here, does the degree of freedom is 1? No. In requiring that CLB is equal to CSB, we have exhausted the degree of freedom. Hence, T is automatically fixed. So, degree of freedom is actually 0. You can observe all these details of this diagram and clarify your doubt. Another more variations of isomorphous system. Elevation in the melting point means that the solid state is more stable. That is, crudely speaking, the ordered state is more stable. Ordering reaction is seen in the at low temperatures. Depression in melting point means the liquid state that is disordered is more stable. The phase separation is seen at low T temperatures. So what results is phase separation can be thought of as the opposite of ordering. In ordering, compound formation occurs for negative values of delta H mixture. This is the descriptions of these two diagrams, which case 1 and case 2 represents. The congruent melting alloy melts at the particular temperature. Above this liquid, below this solid, and the same is this. So you can observe the elevation of melting point here and depression of melting point here, which I have just explained. Some more examples of isomorphous systems with phase separation. You can pause the video and observe it very carefully. So now this is the diagram showing equilibrium cooling. So the above figure represents the very slow cooling under equilibrium conditions of a particular alloy 70A and 30B will now be studied to observe the phase changes that occur. Now let us discuss about equilibrium cooling. This alloy at temperature T0 is a homogeneous single phase liquid solution A and remains so until temperature T1 is reached. Since T1 is on the liquidus line, freezing or solidification now begins. The first nuclei of solid solution to form alpha 1 will be very rich in the higher melting point metal A and will be composed of 95A and 5B. This is given by the tie line rule. Since the solid solution in forming takes material very rich in A from the liquid must get richer in B. Just after the start of solidification, the composition of the liquid is approximated as 69A and 31B. When the lower temperature T2 is reached, the liquid composition is at L2, the only solid solution in equilibrium with L2, and therefore the only solid solution forming at T2 is alpha 2. Applying the tie line rule, alpha 2 is composed of 10B. Hence, as the temperature is decreased, not only does the liquid composition become richer in B, but also the solid solution. At T2, crystals of alpha 2 are formed surrounding the alpha 1 compositions cores and also separates dendrites of alpha Z. See the figure below. You can observe these details. Equilibrium cooling, let us further describe in detail. In order for equilibrium to be established at T2, the entire solid phase must be a composition alpha 2. This requires diffusion of B atoms to the A-rich core not only from the solid just formed but also from the liquid. This is possible in crystal growth. See, the composition of the solid solution follows the solidus line while the composition of liquid follows the liquidus line, and both phases are becoming richer in B. At T3, that is point D, the solid solution will make up approximately 3/4 of all the material present. Finally, the solidus line is reached at T4 and the last liquid L4, very rich in B, solidifies primarily at the grain boundaries, that is depicted by E. However, diffusion will take place and all the solid solution will be of uniform composition alpha, that is having 70A and 30B, which is the overall composition of the alloy, which is depicted by figure F. There are only grains and grain boundaries. There is no evidence of any difference in chemical composition inside the grains, indicating that diffusion has made the grain homogeneous. So equilibrium cooling, the very slow cooling under equilibrium conditions of particular alloy 65 copper and 35 nickel will now be discussed. So this is the copper nickel phase diagram. So details of it are being discussed here. A is the homogeneous single phase liquid. A is the homogeneous single phase liquid. B is on the liquidus line where solidification now begins. This point is on liquidus line where solidification begins. C is solid surrounded by liquid crystals. This C point is between solidus and liquidus. Solidus and liquidus. So it is surrounded by liquid crystals. And D is on the solidus line. That means solidification now ends. D point is on solidus line. So here the solidification ends. And E is homogeneous single phase solid solution. E point is homogeneous single phase solid solution. I hope I am explaining it very carefully and you are listening it very carefully and understanding it clearly. So now let us discuss about non-equilibrium cooling, that is coring. In actual practice, it is extremely difficult to cool under equilibrium conditions since diffusion in the solid state takes place at a very slow rate. It is expected that with ordinary cooling rates, there will be some difference in the conditions as indicated by the equilibrium diagram. You can refer this diagram, the details of which are being discussed. Consider again 70A and 30B alloy. Solidification starts at T1 forming a solid solution of composition alpha 1. At T2 the liquid is L2 and the solid solution now forming is of composition alpha 2. Since diffusion is too slow to keep pace with crystal growth, not enough time will be allowed to achieve uniformity in the solid and the average composition will be between alpha 1 and alpha 2, say alpha trace 2. Non-equilibrium cooling, that is coring, as the temperature drops, the average composition of the solid solution will depart still further from equilibrium conditions. It seems that the composition of the solid solution is following a non-equilibrium solidus line alpha 1 to alpha dash 5 shown dotted in the figure. The liquid, on the other hand, has essentially the composition given by the liquidus line. Since diffusion is relatively rapid, in liquid. At T3, the average solid solution will be of composition alpha-3 instead of alpha-3. Under equilibrium cooling, solidification should be complete at T4. However, since the average composition of the solid solution alpha-4 has not reached the composition of the alloy, some liquid must still remain. Applying lever rule at T4 gives alpha-4 is equal to 75% and L4 is equal to 25%. Therefore, solidification will continue until T5 is reached. At this temperature, the composition of the solid solution alpha-5 coincides with the alloy composition and solidification is complete. The last liquid to solidify L5 is richer in B than the last liquid to solidify under equilibrium conditions. The more rapidly the alloy is cooled, the greater will be the composition range in the solidified alloy. Since the rate of chemical attack varies with composition, proper etching will reveal the dendritic structure microscopically, which is seen in this picture. The final solid consists of a cored structure with a higher melting central portion surrounded by the lower melting last to solidify shell. The above condition is referred to as coring or dendritic segregation. To summarize, non-equilibrium cooling results in an increased temperature range over which liquid and solid are present. Since diffusion has not kept pace with crystal growth, there will be a difference in chemical composition from the center to the outside of the grains. The faster the rate of cooling, the greater will be the above effects. I hope it is very much clear to you all. The dendritic or coring structure is used and asked in many questions, almost every exam. So be clear about that. So now let us consider about copper nickel phase diagram case. In first, A2 solidify has C solid is equal to 46 weight% nickel. Last A2 solidify has C solid is equal to 35 weight% nickel. On fast rate of cooling, that is cold structure will be formed. So you can observe this picture. First A2 solidify having 46 weight% nickel and last A2 solidify having less than 35 weight% nickel. You can see the difference. And on slow rate of cooling, equilibrium structure, uniform C solid having 35 weight% of nickel will be formed. So this is the difference depicting the coring and non-coring, that is cored and non-cored or equilibrium structure. The physical and chemical heterogeneity produced by non-equilibrium cooling rates impairs properties. Cold structures can be homogenized by annealing. For instance, an ingot may be heated to a temperature just below the solidus temperature where diffusion is rapid. The temperature must be selected with care because some regions might be rich enough in low melting point metal to cause localized fusion. However, when practicable, it is more effective to cold work a cold structure before annealing. This treatment has three advantages. First, dendritic structures are broken up by deformation so that regions of different composition are intermingled, reducing the distances over which diffusion must take place. Second, defects introduced by deformation accelerate rates of diffusion during the subsequent anneal. Third, deformation promotes recrystallization during subsequent annealing, making it more likely that the cast structure will be completely replaced by a generation of new equiaxed grains. Here, hot working is also capable of eliminating the coring. Now let us discuss about homogenization. Cored structures are most common in S-cast metals. From the earlier discussion of the origin of a cored structure, it is apparent that the last solid formed along the grain boundaries and in the interdendritic spaces is very rich in the lower melting point metal. Depending upon the properties of the lower melting point metal, the grain boundaries may act as a plane of weakness. It will also result in a serious lack of uniformity in mechanical and physical properties and, in some cases, increased susceptibility to intergranular corrosion because of preferential attack by corrosive medium. Therefore, for some applications, a code structure is objectionable. There are two methods for solving the problem of coring. One is to prevent its formation by slow freezing from the liquid, but this results in large grain size and requires a very long time. The preferred method industrially is to achieve equalization of composition or homogenization of the code structure by diffusion in the solid state. At room temperature, for most metals, the diffusion rate is very slow, but if the alloy is reheated to a temperature below the solidus line, diffusion will be more rapid and homogenization will occur in a relatively short time. Now let us discuss about zone refining. Extreme purification of a metal can radically improve properties such as ductility, strength and corrosion resistance. Zone refining was devised by W. G. Fan, its development being driven by the demands of the newly invented transistor for homogeneous and ultra-pure metals, example silicon and germanium. The method takes advantage of non-equilibrium effects associated with the pasty zone separating the liquidus and solidus of impure metal. Considering the portion of figure in the next slide, where addition of solute lowers the liquidus temperature, the concentration of solute in the liquid Cl will always be greater than its concentration Cs in the solid phase. That is, the distribution coefficient K is equal to Cs divided by Cl is less than unity. If a bar of impure metal is threaded through a heating coil and the coil is slowly moved, a narrow zone of melt can be made to progress along the bar. The first solid to freeze is purer than the average composition by a factor of K, while that which freezes last at the trailing interface is correspondingly enriched in solute. This is the binary phase diagram for nickel copper system showing the extended solute solubility which I have just explained. A net movement of impurity atoms to one end of the bar takes place. Repeated traversing of the bar with a set of coils can reduce the impurity content well below the limit of detection, that is less than 1 part in 10 to the power 10 for germanium. Crystal defects are also eliminated, that is Fan reduced the dislocation density in metallic and semi-metallic crystals from about 3.5 into 10 to the power 6 per square centimeter to almost zero. Zone refining has been used to optimize the ductility of copper, making it possible to cold draw the fine gauge threads needed for interconnects in very large scale integrated circuits. My dear friends, with this I take my voice to rest, and I hope you like the content and found the video worth. So please don't forget to like, share and subscribe the channel. Here I am very much thankful to all my subscribers who believe in me and like my content. So for others who have not yet subscribed my channel, I request all of them to please do subscribe my channel, and please do visit my channel repeatedly and regularly and watch all the videos available there from start to finish, so that you can gain complete knowledge about the topic, as gaining less knowledge or having little knowledge is more dangerous than having no knowledge. And also I request you to share this content with your friends, so that others can also gain knowledge about the topic. And also remember to press the bell icon so that you can get the notification of the new videos promptly. If you want to see and watch further videos from me and get notified, so do press the bell icon. So my dear friends, I am very much thankful to all of you for watching this video. So do visit my channel repeatedly and regularly, and do like, share and subscribe. Thank you very much. Thank you for watching. See you in the next video very soon. Thank you.